Material Science and Engineering Lesson 2, Properties and Characteristics of Materials. ABS, or acrylonitrile butadiene styrene, is a tough, resilient, and easily molded material. It is usually opaque, although some grades can now be transparent, and it can be given vivid colors. Their typical uses are in safety helmets, camper tops, automotive instrument panels, and other interior components, pipe fittings, home security devices, and housings for small appliances, communications equipment, business machines, among others. They are usually sold under trade names like Claradex, Corn Alloy, Glycogel, Glycolac, Hanelac, Lasilac, Lupus Lustron ABS, among others. You can see here in the presentation part of a record of the properties of the engineering material ABS. We have the general properties, mechanical properties, thermal properties, electrical properties, and eco properties. If you can recall, the families of materials like metals, polymers, ceramics, and so forth, which are introduced in the previous topic. What do we need to know about them if we are to design with them? That is the subject of this topic. It is not in the end a material that we seek. It is a certain profile of properties, the one that best meets the needs of the design. Properties are the currency of the materials world. They are the bargaining chips, the way you trade off one material against another. By the end of this lesson, you should be able to describe the importance of material property in material selection, list the material properties and their units of measurement, and evaluate the properties of material needed for mechanical engineering applications. This will be the outline of this presentation. Let's start first with the material information for design. The engineer in selecting materials for developing design needs data for the material properties. Engineers are often conservative in their choice, reluctant to consider materials which they are unfamiliar, and with good reason. The data for the old, well-tried materials are established, reliable, and easily found. Data for newer, emerging materials may be incomplete or untrustworthy. Yet innovation is often made possible by new materials, so it is important to know how to judge the data quality. If you're going to design something, what sort of material information do you need? This chart in this presentation shows the types of material information. We have the raw data, the raw information, and the knowledge. This chart shows the types of material information. We are interested here in the types found in the center of this schematic, which is the structured data for design, or the allowables, and the characteristics of a material that relate to its ability to be formed, joined, and finished, records of experience with its use, and design guidelines for its use. To design material, you need to know its real characteristics. What is its strengths and its weaknesses? How do you shape it? How do you join it? Who has used it before and for what? Did it fail and why? This information exists in handbooks, is documented as design guidelines, and is reported in failure analysis and case studies. It consists largely of text, graphs, and images, and while certain bits of it may be available for one material, for another they may not. It is messier, but it is essential in reaching a final selection. Aside from that, other considerations are the standards and codes that the material should meet, whether it's economically viable, its performance, consumer appeal, and also the cost. In this table, we can see the basic design limiting material properties under usual SI units. We have for the class the general, mechanical, electrical, thermal. We also have the optical and the eco properties of the material, the sample properties and their symbols and units. Take a look at these examples. How would you describe the property of a material that are needed in this application? in a steering wheel mechanism, in a wind turbine, in rocket launching, in railway. Maybe by now you are already reflecting what material these applications needs. In order to answer that question, it is important to discuss the different properties of engineering material beginning with the general properties. The general properties of the material, say for example for ABS, includes its density and the price. Density is defined as the mass per unit volume of the material, and this determines whether how the weight of the finished product would also be. Price, of course, is an important general property. It fluctuates and depends also on the quantity that you want and as well as on your status, whether you're a preferred customer with your chosen vendor. Despite this uncertainty, it is very useful to have an approximate price in the early stage of your material selection. A team of researchers at MIT has designed one of the strongest lightweight materials known by compressing and fusing flakes of graphene, a two-dimensional form of carbon. The new material, a sponge-like configuration with a density of just 5%, can have a strength of 10 times that of a steel. Now that we're done with the general properties of material, let's proceed to the mechanical properties. Part of the record of the properties of engineering material is shown for ABS. As you can see here, the mechanical properties of ABS includes the Young modulus, yield strength, tensile strength, elongation, hardness, fatigue strength, and fracture toughness. These are just some of the mechanical properties of engineering materials. In order to better understand the mechanical properties of material, it is first important to be familiar with a stress-strain curve. So the stress-strain curve is a curve that shows the relationship between the strain and the stress that a material undergo during its operation. So we have here the different components of the stress-strain curve. Say for example, for this ductile material. So when we say strain, this is the change of the length of the material per unit length of the material. While the stress on the other hand is the force per unit area applied to the material. In this stress strain curve, we can see here, this slope here, then we have the yield strength at this point, then we have here the tensile strength, the maximum point, and then we have here the point of rupture of the material. We will describe each of the mechanical property of the material, beginning with the elastic modulus. The elastic modulus E with a unit of gigapascal or giganewton per meter squared is the measure of the material's resistance to being deformed elastically when stress is applied to it. It is the slope of the initial linear elastic part of the stress-strain curve, as you can see here in the figure. The Young's modulus, denoted by symbol E, describes the response of the material to the tensile or compressive loading. The shear modulus, on the other hand, is the response of the material to shear loading. And finally, the bulk modulus is the response of the material to hydrostatic pressure. In an isotropic material, the moduli are related in the following equations, where E there represents the elastic moduli, G represents the shear moduli, and K represents the bulk modulus. Let us have an example in estimating the moduli. The Young's modulus E for copper is 124 gigapascal. The Poisson ratio V is 0.345. What is the shear modulus G? Inserting the values of E and V in the central equation, we can get G as 46.1 gigapascal. The measured value is 45.6 gigapascal based on standard or tabled value, so the difference is only 1%. So it is appropriate, it is okay that we use the equation in estimating the moduli if we are given with the Poisson's ratio as well as the other modulus. The second mechanical property that we will examine is the yield strength. The yield strength is the maximum stress that can be applied before a material begins to change its shape permanently. So in the stress strain curve, it is found here in this portion that you can see here. It is right after our uh, slope here, which is equivalent to the elastic moduli. For metals, the stress at which the stress strain curve for axial loading deviates by a strain of 0 to 0.2% from the linear elastic line. It is the same in tension and also for compression. For polymers, the yield strength is the stress at which the stress strain curve becomes markedly nonlinear at a strain typically of 1%. Polymers are little stronger in compression than in tension. For ceramics and glasses, the yield strength is equivalent to the fracture strength in tension and equivalent to crushing strength in compression. For ceramics and glasses, the crushing strength is 10 to 10 times greater than the fracture strength. That is also the reason why it is more difficult to crush ceramics and glasses than to fracture it. The figure here represents the stress strain curve for metals, for polymer, and also for brittle ceramic. As you can see, the stress strain curve differs for this different family of engineering material. Then we have the flexural strength. When a material is difficult to grip, as is a ceramic, its strength can be measured in bending. And this is done using the measuring of the flexural strength, also called the modulus of rupture. It is the maximum surface stress in a bent beam at the instant of failure. Say for example, you have here in the diagram the deflection versus force. The MOR is the point wherein we achieve the maximum surface stress before it fails. So that's our flexural strength. Then we have the tensile strength. It is the ability of a material to resist a force that tends to pull it apart. For brittle solids, ceramics, glasses, and brittle polymers, it is the same as the failure strength in tension. For metals, ductile polymers, and most composites, it is greater than the yield strength by a factor of between 1.1 and 3. So in the stress strain curve, we can see the tensile strength in this region. So this is for a ductile metal. Then we have the endurance limit. Cyclic loading can cause a crack to nucleate and grow in a material, culminating in a fatigue failure. The stress below which a material can endure an infinite number of repeated load cycles without exhibiting failure is called the endurance limit. Say for example here in this material that you can see in the illustration, the material fails after 10 to the power of 7 cycles, and this is the endurance limit of this material. This endurance limit is also known as the fatigue. Tensile and compression tests are not always convenient. A large sample is needed and the test destroys the material. That is why it is important to have another way to ascertain the property of the material using what we call the hardness. The hardness is the resistance of a specific material to a localized plastic deformation or indentation. The hardness test gives an approximate non-destructive measure of the strength. So it is also defined as the resistance of a material to scratching, abrasion, or cutting. The hardness is measured by pressing a pointed diamond or hardened steel ball into the material surface. The hardness is then defined as the indenter force divided by the projected area of the indent. It is related to the yield strength by the formula 3 multiplied by the yield strength. So if you have the yield strength, you can get the approximate value of the hardness by multiplying it by 3. In this graph, we can see the commonly used scales for hardness, and they are related to each other and to the yield strength. As you can see here, we have the Rockwell, A, Rockwell, C, we have the Vickers, Moss, and also the approximate yield strength. So in this way, we can convert the different measurement of hardness from Rockwell, say for example, to Vicker or to Moss, and etc. Then we have the toughness and the fracture toughness. It measures the resistance of a material to the propagation of a crack. Although diamond, commonly known as the hardest material in the world, there are actually 6 materials that are harder. Diamonds, though, are still one of the hardest naturally occurring and abundant materials on Earth. But 6 materials all have it beat, including the quartzite, boronitride, lonsdaleite, dyneema, palladium, microalloy glass, Baky paper, and graphene. In proportion to its thickness, graphene is the strongest material known, which is an extraordinary conductor of both heat and electricity, and is nearly 100% transparent to light. Now that we understand the different mechanical properties of material, we are now ready to discuss the thermal properties. You can see here the thermal property of our reference material, the ABS. We have the glass temperature, maximum service temperature, minimum service temperature, thermal conductivity, specific heat capacity, and the thermal expansion coefficient. What does each quantity means? Let us discuss the thermal properties, beginning with the melting temperature and the glass temperature. Both these are directly related to the strength of the bands in the solid. Crystalline solids have a large melting point. Non-crystalline, on the other hand, do not. The glass temperature characterizes the transition from the true solid to a very viscous liquid. On the other hand, the maximum service temperature and the minimum service temperature are defined as follows. Tmax is the highest temperature at which the material can reasonably be used without oxidation, chemical change, or excessive creep becoming a problem in the operation. The minimum service temperature, on the other hand, is the temperature below which the material becomes brittle or otherwise unsafe to use. Then we have the specific heat. We all know that it costs energy to heat a material. So the energy that's needed to heat 1 kilogram of a material by 1 Kelvin is known as the specific heat. The measurement is usually made at constant pressure or atmospheric pressure, so it is given the symbol Cp. When dealing with gases, it is more usual to measure the heat capacity at constant volume or Cv. And for gases, this differs from Cp. Then we have thermal conductivity, which is the rate at which heat is conducted through a solid at a steady state. When heat flow is transient, the flux depends instead on the thermal diffusivity. Linear thermal expansion coefficient. Most materials expand when they are heated. So it's important to define this quantity, which is the thermal strain per degree of temperature change of the material. Thermal shock resistance is the maximum temperature difference through which a material can be quenched without damage. You can see here in an illustration an expansion joint in a road bridge. They are used to avoid damage from thermal expansion. Let's move forward to electrical properties. You can see here the different electrical properties for the material ABS. We have electrical resistivity, dielectric constant, dielectric loss tangent, and dielectric strength. Let us discuss some of this, beginning with electric resistivity. This is the property of a material that measures how strongly it resists electric current. It is more than 10 to the power of negative 8 ohmmeter for good conductors and more than 10,016 ohmmeter for best insulators. Electrical conductivity, on the other hand, is the reciprocal of resistivity. The electric constant is the measure of the tendency of an insulator to be polarized when placed in an electric field. For gases, the electric constant is equals to 1. For insulators, it ranges between 2 to 230. Breakdown potential is the electrical potential gradient at which an insulator breaks down and damaging surge of current flows through it. In 2018, some $469 billion or 427 billion euros worth of semiconductors were sold worldwide, an increase of around 15% over 2017. At $40 billion, memory chips can make up the largest market share. This is just one of the application of the electrical property of material. Semiconductor has a property between insulator and that of a conductor. Then we have the optical properties. The speed of light when in the material is always less than that in a vacuum. A consequence is that a beam of light striking the surface of such a material at an angle of incidence alpha enters the material at angle beta. Thus, we have the angle of refraction. All materials allow for some passage of light, although for some metals it's exceedingly small. The quantity that is used to describe this is the refractive index denoted by the symbol n. It is defined as c over v. C is the speed of light in the vacuum, while v is the speed of light when in the material. Finally, we have the echo properties. For ABS, we can see here the eco properties including the embodied energy and the carbon dioxide footprint. Let us discuss them. Embodied energy is the energy required to extract 1 kilogram of a material from its ores and feedstock. On the other hand, carbon dioxide footprint is the mass of carbon dioxide released into the atmosphere during the production of 1 kilogram of material. It is also important to know this embodied energy and carbon dioxide footprint in order to ensure sustainability in the production of these engineering materials. Did you know that gold miners are among the biggest emitters of greenhouse gases in the mining sector? Although critics generally point to coal miners and iron ore miners. This could also be the reason why gold is an expensive metal, not just literally, but due to its contribution to global warming. In summary, we were able to discuss the material information for design, the general properties, mechanical properties, thermal properties, electrical properties, optical properties, and eco properties of materials.